So let's get started with day number 8, video number 8. This one is about solving linear equations, and the next one as well will be on the same topic. This will be sort of the part 1, easier parts where we can solve and get a particular number as an answer, and the next one will be where we really just have variables in our solutions. Right, so in the previous class, previous video, we talked about, or the previous two, we talked about expanding polynomial expressions and then factoring polynomial expressions and how we can use factoring and expanding to find some arithmetic shortcuts if we don't feel like doing long division, long multiplication, etc., to help us do things in our head. Today will be about a little bit of background. I'll kind of do some kind of formal teaching, I think for the first time in this series, about manipulating equations and just explaining some background stuff. And then a bunch of practice with solving for a single variable. You can see the vocabulary that we'll need here on the side. And then in the next video, we'll be talking about expressions or equations where it's just all variables and we can't solve like with a particular number. We're just kind of rearranging. So we will get to that, but first we are going to talk about manipulating equations. So right, this is going to be the final question that we do in the next video. If you see that like right now and you're confused about how to solve it, then okay, that's why we're doing all of this. If it were a number, if we had numbers there, would you be able to solve it, or is it still confusing? So let's just kind of take a few steps back and just think about kind of some real basics about equations and how we rearrange them or work with them. This is going to sound really simple, but if the thing that we just saw, the problem that I was just showing you, if that seems hard and confusing, then that means that you don't understand these concepts fully that I'm about to explain. So let's get into them. So first, solving something like this here. So I'm sure you can intuitively say, okay, x equals 4, but I just want to explain some background about why all that works here. So I am going to show you first a statement like this. A plus 0 equals A. I hope we agree with that. So for any value of A, this statement will be true. And then also, kind of the same thing, but just written a slightly different way, A minus A equals 0. And this works for any value of A. It doesn't matter what we put there. And I'll come back to that or we'll use that in just a moment here. So let's say x plus 3, and the way that we are like actually doing this, the actual algebra that's happening behind the scenes here, so we start with x plus 3 equals 7, and we would say something like this. So equals 7 plus 0. So if I add 0, I'm not changing anything. The left side and the right side are still equal to each other. We still have that balance that exists. Okay? So then if I manipulate this again and say, well, instead of 0, if A minus A equals 0, I can just change the 0 into some number, plus and minus that same number. So let's say we do x plus 3 equals 7, plus 3 minus 3. Right? So this is still just equal to 0. So it's balanced. Nothing's wrong there. Excuse me. So then let's say we want to look at this a slightly different way. How about instead of adding and subtracting the same thing from one side, why don't we just subtract the same thing from each side separately? So something like this, x plus 3 minus 3 equals 7 minus 3. Still balanced. I'm still doing the same thing on each side here. This doesn't kind of break anything. So at this point, then it's pretty easy to simplify. Plus 3 minus 3 on the left is just 0. X plus 0 and equal to 7 minus 3 is 4, and then obviously x is equal to 4. But this is the idea. So I'm sure we all understand this quite well with numbers, but the exact same concepts apply with letters, with variables like this here. So for the next example, I'm going to do the exact same thing, except we have these letters. We don't know what h is equal to, we don't know what z is equal to, and we'll never know, and that's fine. We just want to rearrange and say x is equal to what? X on the left and everything else on the right side. Okay, so we'll just copy everything we did on the left here. So x plus h equals z, and we can still add 0. Doesn't change anything. H is the problem. We want h to be on the other side of the equation, but how are we going to do that? Well, we can also do x plus h equals z plus h minus h, and then instead of adding and subtracting on the same side, which is still balanced, but instead let's just subtract x plus h minus h equals z minus h, like this, and then we can simplify on the left here, plus h minus h, that's just x. So x is equal to z minus h. Again, we don't know what z or h is equal to in terms of an actual number or anything. But we do know that z minus h will equal x, whatever those numbers end up being. We don't know. But we don't need to know. We have solved for x. We have rearranged this in terms of x. So, okay, so we've seen this whole process before, but basically the reason we are able to do this is because of these two statements here. And really it's because of the 0. We have our operation of addition, and 0 is the additive identity. Additive identity. So for addition, adding 0 doesn't change anything. So a plus 0 is still equal to a. That's kind of the background or the theory about why all this works. All right, let's do the same thing for multiplication. So like this, I'll do it a little faster, but it's going to be almost the exact same thing, except here instead of 0, we have this. A times 1 is equal to a, and then also a over a divided by a is equal to 1. All right, so 3x here equals 7, and we can do then 3x is equal to 7 times 1. And then we have 3x is equal to 7. I don't want to multiply by 1. That's not really helpful. So let's multiply by 3 and divide by 3, keeping everything balanced here. But then also we don't want to multiply by 3. We want to divide by 3 on both sides because we have a 3x and we want this 3 to go over to the right side. All right, so then we will instead do 3x over 3 equals 7 over 3, like this. And then we have our 3 on the left here. 3 and 3 will cancel out, and then x, wrong color, we'll just be left with x there on the left, and on the right we will have 7 over 3. Okay, so we've figured out what x is equal to, and the whole thing that let us do that was this here, 1, because multiplying by 1 does not change anything. And 3 divided by 3 is equal to 1, and we just kind of build from that point. So same thing, let's do here, except we have hx equals z, and we don't know what h is equal to. It's just it's a variable, could be anything. We can use the same process to rearrange and solve for x in terms of h and z here. All right, so hx equals z times 1, hx equals z, right color, so times h divided by h, and then we'll just move one of these to the left, just still keeping our balance here. So instead we write hx over h is equal to z over h, n h, and then simplify on the left is x, and simplify on the right, z over h. So we've done it. We have solved for x in terms of these two other variables. And using this idea here of 1, this here is the multiplicative, just like multiplication, multiplicative identity. Because when we multiply by that thing, the result does not change. Okay, so that's the background. So now let's use this concept and how we are rearranging and moving things from one side of an equation to the other for a bunch of examples. And then we'll eventually come back to that problem I showed you earlier. Okay, so solving for a single variable first. That will be the rest of today. We have 4 sets of examples. 1 and 4 sets of examples here. Okay. So on the left here, 2 over 3, I have these brackets here, and I just want to get rid of those brackets, so I'm going to expand there. So we have 2 over 3 times 3m minus 2 over 3 times 6 equals 5 minus m. 2 over 3 times 3 is, that's just 2, so we are left with 2m there, and 2 over 3 times 6, the 6 over 3 there. So 2, we can think of it like this, 2 times 6 over 3, that's 2 times 6 over 3 reduces to 2 over 1, so that's just 2 times 2, so 4. And 5 minus m. All right, and then just now we need to group things, so we want the m's to be on the same side, and the constants to be on the same side. We have minus m here, so we are going to add m to, we're going to add m to this side and add m to this side, and that will give 3m minus 4 equals 5. And then the 4 also we want to move over to the right side, so we add 4, We have -4, so we do just the opposite operation, whatever that is, +4, and 3 wrong color, and my keyboard just stopped working again. There we go. Back to blue. Okay. So 3m is equal to 9. And now we have this 3 that we want to be over on the left. So we will divide both sides by 3. And the left, that cancels out. We're left with m, and 9 over 3 is just 3. So there we go. So whatever operation we have, let's highlight that in here. So we had -m, and we wanted to do the opposite of this, so we did +m. We had -4, and we wanted to do the opposite, so +4. We had 3 times m. We didn't write like a multiplication dot there or anything, but we understand that's multiplication. So so we divided both sides by 3. That's the opposite operation there. Okay, that's that one. Nice and slow, lots of detail. Let's do one at a more regular speed here. I'm going to rewrite this in the middle. 1 over 3, 6u plus 7 minus u. All right, so I'm multiplying, expanding the brackets here. So 1 over 3 times 6 is 2. 2u, and 1 over 3 times 3 is 1. And that is equal to 7 minus u. If I move the u's over to the left here, that will give me 3u. And I move the constant over to the right, that will give me 7 minus 1, 6. And u equals 2. So there's our answer there. All right, and your turn with this one. Please solve for x. All right, our solution here at the end is x is equal to, check my notes, 4 is what I got as my result. Hopefully you got the same thing here. All right, next one's just a bit more practice with this, where our equations are a little bit larger or more complex. So let's say we look at something like this. 4q plus 3 over 2 plus 6 equals 3q plus 5 over 4. So a few different ways we could do this. We could rearrange this and say these fractions here, and we can just split them up. So we could do something like this and say 4q over 2 plus 3 over 2 plus 6 equals 3q over 4 plus 5 over 4. And then gather the q terms, gather the constant terms, and simplify and everything. That's one way. I think what I personally would prefer for a question like this is we can find the lowest common multiple, multiply the whole thing by that lowest common multiple, and then get rid of the fractions, and then it will be easier to kind of move things back and forth. So I can notice here I have a 2 and a 4 lowest common multiple there, which we talked about 2 days ago with the prime factorization stuff. Lowest common multiple is 4. So let's just multiply both sides by 4. Yeah, I'll write that out as an extra step here. 4q plus 3 over 2 plus 6 equals 4 times 3q plus 5 over 4. All right. So 4 times this thing times the something over 2 just means 2 times that whole thing. So that will be 8q plus 6. And then 4 times 6 is 24. And then 4 times something over 4. The 4's just canceled out. So we are just left with 3q plus 5. All right, we'll gather our terms. 8q minus 3q. Let's do that as an extra step as well. 8q minus 3q. And then we will have 5 minus 6 minus 24. And we just simplify. We will get 5q here. 5 minus 6 minus 24. That looks like negative 25, and q equals, therefore, or divide both sides by 5, and then we get q equals negative 5. If we want to check our work, of course, we just take this value of q equals negative 5 and substitute it back in to our original equation and just make sure that the two sides are still equal. I will leave that step for you guys to do. Okay, so that's one with fractions here. We'll do another example. I'll do it the other way. Excuse me. In the next example for variety. So my turn here. 3r plus 5 over 6. 1 for r plus 3. 6. Better. Okay, so I'll split this up. 3r over 6 plus 5 over 6 plus 1 equals 4r over 3 plus over 3. All right, if we simplify this, then that's r over 2 plus 5 over 6 plus 1 equals 4 over 3r. I am going to have to multiply back anyways. Let's take a few steps back. Let's not reduce that. So 3r over 6, and let's say the 4r over 3, that will move to the left, so minus 4r over 3. And moving our other terms over, we have 3 over 3, that's just 1. And we have minus 1 here from the left side, and also a minus 5 over 6 here. Okay, so left side is just negative 5 over 6, and the right side, left side, we will need to change the denominator to our lowest common multiple, which will be 6. So 3r over 6 minus 8r over 6. Now we can subtract those directly, and we will get negative 5r over 6 and negative 5 over 6. Running out of space. Haven't had that happen yet. Okay, so I'm going to multiply both sides by 6, which just eliminates the fraction there at the bottom. So negative 5r equals negative 5. And then I will divide both sides. Yes, I will divide both sides here by negative 5. And then -5 divided by -5 is just 1. So there is our result. That's why I prefer to get rid of the fractions first. Splitting them up like this works, but it's kind of a bit longer. Anyways, 2 options, your choice, whichever one you prefer. Or, excuse me, this next question here. Go ahead. All right, and our solution here at the end, hopefully you got s is equal to -8. That's the solution that I got. Okay, that's that example. That set finished. 2 more sets here. The next one just with decimals, so nothing too crazy here. A few different options. We could look at the decimals, or we could change the decimals into fractions and then do what I did on the previous example and try to just kind of add, subtract the fractions, whatever. We could change it to fractions and then multiply by something to get rid of the fractions and then solve from there, like we did 2 examples, like I did 2 examples ago. We could look at the decimals, and if we can see it right away, we can just directly multiply by something to get rid of the decimals and then solve. And I can look at this and say it would be 20. If I multiply by 20, all these decimals will disappear. Or we can just leave the decimals and use them. They're not that hard to deal with. So I'll choose that method. So let's expand the the brackets that we have here. So 0.25x plus 0.05x plus 0.15 is equal to 2.85. Okay, and then if we add up the x's here, we will get 0.3x and gather the constants, 0.15 or 2.85 minus 0.15, that will be 2.7. Okay, so also at this stage we could say let's multiply by something to get rid of the decimals, like 10, or we could and then we would factor down from there, take out a common factor of 3. Again, lots of options. I think I will just do division here and say x is equal to 2.7 over 0.3. And we dealt with these before. So this is the same, 2.7 over 0.3. Just multiply the top and bottom by 10. That's the same as saying 27 over 3. 27 over 3 we can probably right away recognize. That's just 9. So x is equal to 9. And our solution. Okay, let's get rid of this. And next, my turn here. Do one quickly. All right, n, so 0.25 n plus 0.05 n plus 0.25 equals 2.95. All right, kind of similar numbers to the last time. 0.3n is equal to 2.95 minus 2.5 is 2.7. Actually, very similar numbers to the last time. But let's do a different method here. Let's say 3n is equal to 27. Multiply both sides by 10. Then divide by 3, and 27 over 3, 9. Okay. A little unusual that the numbers are quite that similar, usually not almost identical like that, but anyways, two different methods. So your turn with this one. All right, our solution here, final solution that I got was wrong color. D is equal to, try that again, D is equal to 16. Hopefully you got the same result. All right, let's move on. Quick thing to explain, and then one more set of problems, and then that will be it for today. Okay, so some terms here to explain conditional equation, identity, and contradiction. I've already kind of explained what an identity is, but let's just go in order. So a conditional equation is something like this: x plus 2 equals 5, where if x is equal to 3, then the left side is equal to the right side. So then we would get 5 is equal to 5. But it's only true in that situation. So if we have x is equal to 1, then that's 3 equals 5. That doesn't work. If x is equal to 10, that's 12 equals 5. That doesn't work. That doesn't make sense. So it's only true for one particular value of x. That is the situation that we will have most of the time for most equations, but it doesn't always work out that way. We can have a situation like this one where we have simplified, that's just 4x is equal to 4x, and if we simplify some more, that's just 4 is equal to 4. Well, the variable is gone, so there's no variable creating a condition, so it's just always true. So conditional equations are, do this in blue here, sometimes true. Identities, like this, are any statement that is always true. Just like I said, the additive identity, for example, a plus 0 equals a, that's an identity because it's always true. There is no value of a that makes this a false statement. Always true. And then the last one here, if we take a look at this and rearrange, we would get 3x is equal to 3x plus 6. And then if we kind of move the 3x over to the other side, we get 0 is equal to 6. But 0 is not equal to 6. So for this kind of statement, it is never true. It is impossible to make that work. There's no value of x that we can choose that will make the left side equal to the right side. So most of the time we will get a conditional equation like this, but sometimes we can have an identity where it's always true, and sometimes we can have a contradiction where it is never true. We need to be aware of what those situations look like, and if we get that as our answer for something, then not to be shocked or think that we did something wrong, but understand that's one of the possibilities. So there's our fancy names for them: conditional equation, an identity, or a contradiction. So last set of examples, we'll just look at these and solve them and see what type they are. Are they a conditional equation with just like a regular like m equals something value, or are they an identity, always true, or a contradiction, never true. Okay, let's take this and I will expand the brackets here. 5m plus 27 plus 9m, and on the right side 2 times 7, 14m minus 22. Okay, so 5m plus 9, let's just gather first. So 5m plus 9m minus 14m, and on the right side we have negative 22 and not plus, minus 27. So the left side 14m minus 14m, that's just 0, and on the right side, well, not 0, we have a negative 49 here. Yes. Okay, just making sure. Same thing in my notes. So, the left side is not equal to the right side. And it's not a sometimes thing, just never. It will never work out. So this is a contradiction. There's another way of saying there is no solution, or it is impossible to solve this. Okay, that's this example. Let's look at another one. My turn here. Right, expanding again. So 4 plus 27x minus 973 equals negative 42x minus 13 plus 3 times 23, 4669 x and minus 46. Okay, so let's gather our x's. We have 27x plus 42x and then minus 69x. And on the right side, we will have negative 13 minus 46 and minus 4 and plus 63. Okay, so very kind of suspiciously or conveniently, the x's are just disappearing here. 27 plus 42 is 69, minus 69, that's just 0. On the right side here, 13 minus 46, that's 59, minus 4 is negative 63, plus 63. So that's also 0. Okay, so the left side and the right side are equal and they are constants. Doesn't have to be 0. It could be like we had 4 equals 4 or 20 equals 20 or something, but there are no variables. The variables all eliminate. So this means we have an identity, which again is saying that it's always true, or there are an infinite number of solutions. Any value of x that you put in here will work out and will make this a true statement. Okay, so that's that one. And last practice one here for today. This is your turn. Have fun. Okay, what I got for this one was a contradiction. When I simplified, the d's disappeared, so I ended up with 0 equals 98. But of course that is not true, so a contradiction. So that was my solution here, my result. Hopefully you got the same thing. Okay, I'll just show you some practice problems and then that's it for this one. So just solving linear equations, nice simple ones here. These are all in chapter 2.1. Excuse me, 2.1 from our intermediate algebra textbook. 5 exercises 5 to 30 here, just about solving linear equations, nice simple ones. Next, classifying equation types. So what we just did as a conditional or identity or a contradiction. Those are here. Then linear equations involving fractions, these practice ones, and involving decimals, these practice ones here. So lots for you to practice. Wrapping up, we've talked about additive identities, multiplicative identities, and then conditional equation identity contradiction. So some vocabulary terms to remember from today. We started off with kind of the background theory stuff and manipulating equations. And then most of the practice was solving for a single variable. We'll continue this stuff in the next video, talking about rearranging formulas where we don't have many or perhaps any actual numbers. It's all just variables, and practice kind of rearranging and solving for a particular variable within a formula or a larger equation. And then the problem I showed you at the very beginning of today, we'll get back to that one. Sorry, this is day 6. I'm not sure. Should not say day 6. That should say day 8. Okay, let's pretend that didn't happen. So finish day 8. Thank you for watching, and I will see you soon for day 9 and more about solving and rearranging linear equations.